Can you hear me in the back? Yes, all good. Great, welcome to the lecture. So this is the lecture before the last lecture. We have one more week to go. And next week I will talk a little bit more about the exam information. What should you expect in the exam and what kind of question types that you might have. We'll have some example questions as well. But before we start today's topic, I would like to recap on the last week, which was the first week that we started discussing machine learning. And we covered a general brief overview of machine learning and tasks that would be classified as machine learning. And also we will develop on this idea today and next week. Which we will cover regression this week, and next week we will have a topic of clustering and unsupervised learning. And that will hopefully give you enough overview of machine learning to develop further. So these three topics are the fundamentals of machine learning, but by no means they are a complete picture of machine learning. There are so many different topics and subfields. If you're interested, you should study yourself and also review different material, including online courses or tutorials. If you are interested and you cannot find good structured information, I can also suggest you some good textbooks as well to read out upon the details. But anyhow, let's discuss from last week. So what is the general principle of machine learning, and how is it different than the methods or algorithms that we covered throughout the semester? How is it different than search or probabilistic reasoning or representation or identification problem like we discussed in constraint satisfaction problem? What is the methodological difference between machine learning and traditional AI methods? What makes it special, or what makes it different? Anybody remember? And don't be scared to go back. You know, there are plenty of seats here, so you can probably more easily see the screen. And I had some Anas?
Yeah, I mean, it's the learning part. It improves.
Okay, but how? How does it learn?
Through being told if something is correct or not.
But how you are telling the algorithm what is correct or not? Are you giving instructions? Are you giving the code snippets, or?
We just give data and then ask them to find patterns inside and then look at rules and stuff until they can figure out something.
Okay, so what's your name?
Louis.
Okay, I think I'm seeing you first time. Good, Luis. So Luis is right. So machine learning works differently, that it actually works on data. It learns from data. So rather than traditional AI or programming, which we give instructions, but in machine learning, actually we don't give predefined code or instructions. It learns from data itself. So it learns the patterns existing in the data. So that's how it actually learns, and it's quite different than other methods. Because in typical computer science or AI algorithms, you have to, as a programmer or whoever designing the algorithm, have to give the instruction and the path in a sequence, right? And so it goes through the sequence line by line and all the steps to execute it. But in machine learning, code itself doesn't even matter. The data is actually what the source of knowledge is. And algorithms learn from that. Okay, great. And what is the general task of classification? What are we trying to do in a classification? goal of classification? We briefly gave some examples: classification, reinforcement learning, and also regression. What are we predicting? Agatha?
Classification using like the more general questions, like try to, based on the answers on the questions, to classify the person or case to something more known.
Mhm. So what is it specific about the output that we are predicting? What is it, the property, the important property a classification output should have?
That it's giving us more or less accurate answer. That,
Mhm.
for example, if you are asking if that person will pay back the
Yes.
credit,
Mhm.
we will get more or less the information yes or no.
Yes, so,
That we don't know. So
yes. So actually you kind of mentioned that, the options that we are predicting matter for classification, right? It must be countable categories or countable number of items that we need to predict. If this is countable number of items or labels in machine learning term that's being predicted, it's called classification. So then it kind of is related to today's topic. What about regression? What is specific about the output for regression? So if classification is countable number of categories, what would be the concept or the output property for regression? Continuous numbers, right? If your output or the label that you're predicting is continuous, it becomes regression. If it's countable number of categories or labels, then it is classification. That's the basic process. But can anybody remind me how the training works? Like, or let me just say this: how do you know that the machine learning model that you are training is good or not? What is the methodology that we follow in machine learning? Correct? What was your name again? Leo?
Diego.
Oh, Diego. Diego. The decision tree is an example, but what's the methodology? Like, in general, classification or regression, how do we go ahead, Dennis?
You ask it some questions that you already have the answer to, and then you compare your answer to its answer.
Exactly. So it's like a two-phase, two-step training, right? First, we train the model based on known information that we have the labels already collected, which maybe some experts annotating the data. Then in the second phase, we test the performance of the model that we just trained. Is it good or not? How do we do that? We basically hide the output, as Enes mentioned. We just make the algorithm predict, and we compare against our existing labels, whether it's doing correct job or not. And then based on the accuracy, we can say that the model is good or model is bad. Okay, good. This is same process for all the supervised machine learning algorithm. Anybody remember what's unsupervised learning? So this is the methodology used for supervised learning, which is classification or regression. What about unsupervised learning? Name might ring some bells. This is unsupervised. Go ahead, Luis.
We don't say anything to the machine and do it alone, I guess. Not supervised.
Yes. Supervision is basically giving the output labels, right? If you don't give output labels, it's not supervised. So it will actually come up with some kind of learning which will show you how the patterns are represented in data. So basically, without giving the labels, we just run the method or algorithm on the data. So because we don't have labels, it's not two-phase like we did in Supervisor, is actually giving all the data and seeing what kind of groupings or what kind of clustering exists in the data. Okay, so far so good. Great, so let's build on this idea and we will continue on regression and see how it actually works. But even before we go to technical details, what is a model? What is it that we try to learn? How do we represent the reality, or why we have to do data modeling or machine learning modeling? A model is, go ahead, do you have, Rebecca?
Models because putting every detail that we have from the real world into like to learn something specific would be overkill, you could say. It could also be our own data. And with creating a model, we can make sure that it is correct and it is just the scope that we actually need. Maybe a little bit more. It can be also abstracted to make it simpler.
Exactly. Models are abstraction of reality. And reality is very complex and messy to work with, right? In real world, physical world, there are a lot of things going on. So many complexities, so many uncertainties is going on. But what we do is we create a model as a simplification of reality, which is an abstraction that we can use to simulate reality to a certain level. As close to reality is better, but of course we do have some assumptions. But it is still better than having nothing, right? So let me give you an example. So you don't actually have, let's say you are a shoe seller, right? You're making shoes and you are selling shoes to customers. And assume that you have no knowledge or historical information about how much should you make, how many pairs of shoes you should sell, right? You have no knowledge, you have no anticipation, you just open the store. So how many shoes will you sell tomorrow? Or how many shoes should you keep in your store? Or how many should you produce, right? There's a lot of uncertainties, right? If you produce so many, you probably won't have enough space in your store, right? So that won't help. If you produce little, maybe you have a lot of demand, but the customers will come, you don't have any shoes left. What should you predict, or what should be the right amount of shoes so that you produce and they sell it as you produce? You don't know, right? But that information is something that you can drive. At least you cannot see the future, none of us can, but as close as we can predict what's going to happen tomorrow, the insight that we do is going to be tremendously helpful than having no information, right? Because we can produce 1 million shoes, or you can produce 10 shoes or 5 shoes. There's infinitely many numbers. So what is it, the right amount that you will have sales tomorrow is the question, because that will make huge difference. So rather than building or manufacturing 1,000 shoes, maybe you will sell 39 shoes tomorrow. So if you can have 39 production or close to 39, you would be in a good shape. So that's the idea. We want to predict the future, but our uncertainty or error from actual quantity should be as close as possible so that our error margin is small. Okay? So our understanding from the past, and if we can learn from historical information, then we can, in a small gap of error, predict the future, which will be still better than having nothing. So if you can have a good estimation about how many customers will visit your store tomorrow, how many shoes or smartphones should you produce, or which stock should you invest, whether it will go up or down. So all of these can be predicted and in a small margin of error. That's our goal. We want to anticipate the future, predict the future, but with as small as possible error margin. Okay, that's the goal. So So what kind of information can be used? For instance, selling shoes or smartphones. What do you think would be reasonable information to know? Anas?
How much you sold yesterday and the week before?
Yeah, that would be useful, right? If you sold maybe 39 or 35 shoes yesterday, you shouldn't expect 1 million to sell next day, right? That would be ridiculous. Or if you sell maybe, a lot in thousands, and then you should expect some numbers in thousands as well. So information from yesterday would be good, but maybe additional information would be helpful, such as what kind of information? Luis?
If there is any festivals in that area for the that is more tourists.
Yeah, absolutely, right? So if you know more information about the surrounding or the dates of holidays, maybe it is a holiday tomorrow and there will be nobody coming to your store. That would be important. Or if there's a festival or people, tourists are coming, yeah, that would be a good thing. Maybe other information as well, right? Seasonality would be important. Yeah.
What shoes are trend on TikTok or Instagram?
Yeah, what shoes are selling most, or many other information, like is it beginning of the month or end of the month, and how much money people have, right? Well, those are information that might be useful, or many other stuff. How many shoes did you sell the same day last year, right? That might be also a good indication. There are many factors that you can take into account. But as more relevant information that you add into the input, your prediction will be as close to the reality, or in theory it should be, right? So if you're predicting number of shoes and your only information is how many people live in the city, that may not be enough, right? So as you incorporate more information or more features, we say, related to the problem that you're solving, your picture of or prediction of reality will be close as possible to the reality, okay? So that's the idea. So we want to collect as close as all important information that we can get for this anticipation. So we do this a lot of predictions intuitively, right? If you are an expert in this field, you might already incorporate some of the information by your historical experiences, or you can get some of the facts from some of the data stores or information. But what we want to be actually more objective and generalizable information derived from the data. So what I'm saying is that we want to know, we want to answer all kinds of information, not only a specific information given that. So we want to create a model that can be used for many different questions. So if I'm interested in knowing how many shoes I will sell in 3 months or 10 days or 3 years, those could also be important to add. But let's get started with a very simple example. So assume that we have this data. This shows how much sales do we make, and this is how much advertisement we made on those products. So amount of sales and amount of advertisement for different products and different information. And what we want to answer is advertisement effective? Does it increase the sales or not? So this is just a snapshot of data. We don't know it yet. It may be or it may not be, just by looking at the numbers, which may not be easy to see. Okay? What can we do? What should we do now? So these are, let's say, millions of kronas in advertisement. These are the amount of sales that you achieved after that. One simple thing we could do is visualization, right? We humans are good at visualization, reading the insights from visualization rather than actual numbers. So if you plot these are the numbers, how much advertisement and how much corresponding sales. There are some sales that are up here, there are some advertisements. So advertising increasing this X dimension and Y dimension is the sales. So what can you say about this? Is advertising effective? Is it increasing the sales? Yes or no?
Sometimes.
Sometimes, yes. How would you come up with that insight? What makes you think that it is effective sometimes?
If we spend more than 10 million or 10.5 million,
Mm-hmm.
then almost all products do best.
Mm-hmm.
And then if we spend less, almost all of them sell less than 130.
Mm-hmm. Good. But in general, in average, what would you say about how much it contributes? Can we quantify, like if you spend this much advertisement, you should expect in average this much increased sales? Is it something we can do it? Yes or no? So maybe we can just first read the data. So if we have sales and advertising, we can see that there are some positive correlation, right? It's going up. So in average, some of them are going down, some of them are going up, but in average, if I were to show you, so some of them are low, some of them are high, there are some gaps, but in average, you will see that there's a positive trend, right? Between sales and advertisement, higher the advertisement, higher the sales in general. So we could see that clearly. But it's still difficult to quantify how much, right? Give a number. What's the contribution of advertisement on the sales? So if I spend $1 on advertising, how much should I expect to get from sales? So that's actually the goal that we want to achieve with the regression. I want to get a quantified number that it shows me this model, very simple abstraction, that if I put $5 in advertisement, I should have $7 in sales in return, or some numbers. That's the hypothetical model that we want to get. So this simple example says, after $10,000 for every advertising dollar spent on product, you get $5 more on sales. This would be an example, right? So this shows you what the data is. So maybe I can just draw me. There's some data. Okay. So we can see that there's a positive trend, right? As advertising is increasing, over time sales are increasing. We can clearly see that. But how much? Let's assume that we exactly know how much, and we can, if we have a data, so we create a model. Let's say this is the model, although it's not perfectly covering all the information, but it's kind of going through all the data, and we could have some anticipation for the average performance. So what would be interested is that some kind of linear representation of this model. So can we, if hypothetically we had a model which is this line itself, how can I mathematically represent this line? What is the equation used for this line itself? Let's say this is alpha. Okay. So y is equal to beta x1 so this would be a linear regression, right? You have a y that that you are trying to estimate is based on coefficients of beta 1, x1, beta 2, x2, blah blah, time plus the alpha. Since we only have two items, we can just make it very simple. So this would be y. So here, this is sales data, and x is advertising, and this is alpha. Okay. So this is the alpha. It's also called intercept. Intercept means that if I have no advertisement, how much sales should I expect? Right? Even if you don't do advertising, you might still have some sales, right? So what is the point that it crosses the y-axis? It should cross through origin as well. If it's the origin, what would that mean? If you don't make an advertisement, you don't make any sales, right? But hypothetically, this could be a number greater than 0. But this could also be 0. So what is this beta? Where do we get this beta? So if you have a linear equation crossing through, don't think about anything on this specific example, but this is your y. How can you estimate this beta? What does beta represent? Yeah, go ahead, Anas.
How much it goes up over
Yes.
how much it goes down.
Exactly. So the ratio of x or y over x, and we have a specific term in mathematics for that.
Rise over run.
Yes, but there's a specific name. What about slope? Right, this is the slope, right? This is the slope of the line, right? And how do you estimate the slope? Difference in y divided by difference in x, right? Okay, good. Basically, all I need to do is so it's just marginal difference ratio between sales over advertising. So the marginal change of y divided by marginal change of x. Simple. And these are called coefficients. Okay, so the goal of regression is to draw this line that minimizes the gap or error. And if we find such line to explain the data, and those information, the coefficients that we can deduct from the data is what we will use. Okay, so, but where should the line go through? So what I'm saying is, how do we come up with what is the best place to cut the data? Okay, and this is regression model is simply finding this equation where we have y equal to beta x1, beta 2 x2 plus plus and alpha. That's the intercept. Now that's the whole idea of the regression. How do we find this particular equation that represents the data well, so that we can use it for any other questions? Let me rephrase this question differently. So this is our same data. This is the original data. how many different lines that I can cross through this data? Infinitely many, right? We can have infinitely many lines. One can go through this, another could go through this way, that way. So infinitely many. But what is the best? In your opinion? Or why do you think it is the best? Or how do you find the best line crossing through this data? Yes?
My intuition would be to sum up the distances of each point on either side of the line and try to make them equal.
Mm-hmm. Cool. That's a good idea. So you would actually, you're saying that I would sum the distance between each point to the line and try to minimize the total.
Yeah, one sum for the bottom and one sum for the top.
Mm-hmm.
And try to make them the same.
Okay. That's a good idea. Any other intuition? Everybody agrees. But distance itself is always positive. But if it's underlined, you would say negative, right? That's,
Yeah, you could try to make it zero.
yeah, okay. So you, instead of taking absolute value, you would just make it positive, negative, directional, and then, yeah. That could be one, right? That could work. Go ahead.
A line that would be near the most values.
Mm-hmm. So you should try to find a line that's near to most of the values.
Correct.
Good. And how would you measure that?
By observing the graph.
Huh?
By observing the graph.
By observing the graph. That's not a bad idea, but manually doing that might be quite challenging. Especially if you have number of dimensions greater than 3. Let's say if you have 4 features, it may not be possible to visualize that, right? That would be challenging, but intuitively that's correct. Is this a good line or good model, the one above? So which one of these 3 better, in your opinion? Is it this one or that one or that one? Let's say this is B, this is C, this is D. And why?
See
C, why is it?
the distance on the points on line below.
Mm-hmm.
I'd say that D, because there's a similar amount of points below and above it.
Mm-hmm. Good. Why not B?
There's only 5 values underneath.
Yeah. A lot of these are lower and there are more amount of them here. Here it is close, but there are more weights on each side than this side. This is more evenly distributed maybe. But we don't have to visually decide that. Can we come up with a metric? This would be helpful. So what I'm going to actually do is, let's just draw this further and we get more. Okay, this is sales, these are advertising. So we should draw a line . So assume this is the line. So can I predict any number? So these are advertisements. Let's say this is 5. This is 10. let's say this is 30, and this guy is 50. In my original data, I don't have any number for 23.5. I have some examples for other numbers, but can I predict what is likely sales should I get if I spend 22.5? Yes, how? What would be the estimate prediction?
You draw a line up until the blue one.
We would draw a line, and the point that we hit the line is our prediction. This is predicted sales for 22.5, right? And that would be our prediction, as simple as that. So in theory, I can have any number of items that I can predict within this range, right? I could predict 21.0.7, or I can predict 5.9, 5.6, any number, which can be done, right? Because this line is continuous. But what would be my error range of prediction? If this was actually supposed to be here, and I predicted this one, so this is let's say this is 29. I predict 29, but it's actually 34. So what happened? I made some mistake. And that mistake made me lose maybe $5 million, right? Or whatever the quantity is, which may be very large. So our goal is to minimize this prediction error, right? If I were to predict exactly, so if it was 29 and I predicted 29, that would be very good. So my decisions would be accurate. So I can make a decision about sales, so that would be nice. So our goal is to minimize the error and maximize the prediction accuracy. But how can we quantify this? So this difference is error, right? Let's say this is error 1. And in machine learning, there's actually a name for this, it's called residual. Residual is simply the gap between the difference. So this is what I predicted, y prime, and this is actual y that it was in the data. So the difference between these points are called residual or error. So I made this much error in this case, but in another case, the data was here and I predicted here, so the error is quite small. This is a very good prediction. But some other points, the error is a little bit bigger. Here, the error is big. But here, not that much. So there are some errors here, there are some errors here. So for every line that I draw, there will be different set of errors. But how do we calculate the total error? How can we calculate the total error? This would be fine, right? We could just sum it up. But because their positions, this might be positive or negative. So maybe we could just make it absolute, right? This could be absolute. Then we actually sum all the number of errors, and we could just minimize it. So we find a line that minimizes the total error, which would be fine. But in order to get a differentiable equation, we usually take the square, right? When you take the square, this is always positive. So distance has to be 0 or positive. But when you take the square, it actually becomes a differentiable function. And that's the whole idea of regression. So this old man, Francis Galton, maybe some of you know his name, is quite famous. He's also known as father of statistics. He invented this formula, right? You can take, this is called least square regression, simply minimizes the total error for a given line. So we draw a line that, so there might be infinitely many lines, but this is the line that minimizes the total gap. So we want to minimize the total error by drawing a line that crosses through all the points and minimizes the gap. And sometimes you would also hear this as the name of least square regression. That's exactly the same. So these are actual or observed data, and these are predicted based on the model. The gap is error or residual, and we want to find all these errors for given data set, and we want to minimize this total error. And the line that we find is actually the line that minimizes the total sum of the error. And for given line, once we actually have this equation, let's say this is 19, and you calculate the slope. You can use the angle of the slope and then find the gap. So for instance, this line would give us the equation such as 19 plus 2.1 times advertising. This is our model based on this data. So what does this mean? If you have 0 advertising, you should still expect 19 sales. Okay? And this is intercept. Intercept is the line that's crossing the y-axis, or when you have 0 advertising, in this example. This is the coefficient or slope of this x1, this line. It means that for every advertising dollar you spend, you should increase the sales by 2.1. This is what it means. This coefficient means that for every dollar spent on advertising, you should expect the output to increase 2.1. Okay, so now we can quantify it. We can say that, okay, if you're spending more advertising, you should expect more sales by this much, or that information. That actually is quite useful. Okay, so the slope of the line is actually the coefficient that we are trying to estimate, and intercept is the point where we cross the y-axis. And you can estimate this. But how do we know if a model is good or not? Okay. So far, so good. Any questions? Clear? Yes. Okay. Okay. What I want to know is how much useful this model was. So I draw this line, and I think that it is actually nice because it captures a lot of information. But is it really good or not? Right? So did it even make a difference? How would we quantify that? So if we didn't do anything, so if I gave you this data, if I gave you original data without any line, if I were to say, can you guess how much, or can you predict how much should I expect in sales if I spend $22.5 on advertising? What would be your best guess? without modeling? If you were to just guess any number. No? So this is your data, original data. If I go to this guy, so this is the data. I have no idea about this model, which maybe, let me show you this. So these are the original points. So I don't know, we could just predict some numbers here, or some numbers here. If you had no idea about the modeling, what would be your best educated guess? What should you predict on sales part? Should you guess something here, something here, or something here?
Something closest to what's around.
Something closest to the average, right? So you would expect something closest to the average of all points on Y, right? If you don't have any model, you could just guess that what's the average of the line. Or that would be Y bar, right? In the simplest term, we would just assume that you should get Y bar. But that's not really sensitive, right? So one way, this would be your model, but that doesn't change for any value, right? For 22 or 30 or 9, you're just estimating that's the average, which is probably not a very sensitive model. Okay, that's not good. And this is your model itself. So how can you know that your model is good enough or not? We can see how much improvement it makes on random guess on average, right? We can see how much it improves based on just Y bar. And that could give us some quantified understanding. So what I'm saying is, so assume this is our original data points. This would be Y bar. This is dumb model, you would say. And we have done something smart like we did on least square regression. And we think this is better than that one. Can we quantify this? Yes, we can, right? So for every point, what was the error range? If I were to use Y bar, how much error would I make? Let's say this is E1 prime. And how much the current model improved this? This is the error I make now with this model. I do this for all of them. Right? This is E2 bar, E2 without bar. And this is E3, and this is the E3 prime. So you would probably notice that error range has reduced. Instead of going all the way to here, now error is made much smaller here for this point, right? Here as well. So these are much smaller than actually going all the way to here. Maybe some points here will make a little bit less error, but in general, these guys will be also less error than going to Y bar. So we could actually quantify that, right? So the original variance, original error range for the Y bar was much larger, but these are the actual error remaining after we have this nice model. Okay? So the error has reduced, error has reduced, error has reduced. So we could compare error that actually reduced. SST is I. This is actual points, actual observations. This is average. Y. This is total error for y bar. This is the original point. This is how much error we had in the beginning. SSE is how much error our model is currently making. This is yi minus y I prime. So this is actual. This is our predicted. So what I'm saying is, so this is actual, this is our predicted. This is actual, this is our predicted. The gap between those two are our model's error. And the gap, the black one, the gap between actual point to the y bar is SST, total error. It was already in the data. Okay? So what we do is simply calculate the difference. The remaining error is simply SST minus SST. So can we quantify actual difference, the error our model made compared to original error? How much better our model is? So in other sense, we could say that SST minus SSE this is called R square. This is very important metric to quantify regression model. It means that how much error was in original variance if we were to guess it, and how much we actually reduced that given our models. So if the gap is more, it should be good, right? So what I'm saying is, if SST was equal to SSE, so our model error is exactly equal to average y bar. What would be the R square? 0. It means that our model did not improve anything. It was exactly the same as SST. It's exactly the same as just y bar. It didn't improve. If it is actually if SSE is 0, when would that happen? Our error is 0. When would that happen?
The line goes to every point somehow.
Exactly. If you have a line that all the points are exactly on our model line, there's no error, right? If our model is so good that it's exactly going all the points in the data, the error would be 0. Total error would be 0. That would be the perfect scenario, right? That would be hypothetically perfect scenario. In that case, what would be SST minus 0 divided by SST? So it would be 1, right? So in other sense, R square is a value expected to be between 0 and 1. If it is 1, it's perfect, because our model exactly goes to the point, all the points in the data, which is rarely happening. But If it gets closer to 1, it's good. If it goes closer to 0, no good. It means that our model actually didn't work much. Okay? So we want to get as close as to 1. So that's a way to measure how our modeling is doing, right? And when you actually run a regression model, you will get an output something like this. So it's basically saying that I'm using advertisement as an input, predicting sales, and these are information. The intercept was 51.84. Advertisement's coefficient, or the slope, is 7.5. So basically, the model says sales equal to 7.5, advertising plus 51.84. This is your model. So if you have this model for any advertising, you can estimate or predict the sales, right? Simple as that. This is the output based on data. But what you can see is there's an information called R square. It says 0.24. It gives information about the quality of model. Is it a good model or not? Maybe good, maybe bad. It depends on the problem. But it's not too high, right? It's better than 0, of course. But it's not very close to 1. So it's okay-ish. It's not too good, but it's okay. If this was a chemical or physical experiment, it's really poor. Because physical science or physical phenomena is more predictable. So you would expect maybe 80%, 90% accuracy or improvement. But if it's a social science problem, it's human decisions and stuff, these are very difficult to predict. You know, polls or some other things that you're trying to predict, which may be okay. It kind of depends on the scenario. But this is how you can quantify models, and you can compare the models as well. Questions? Okay, let's take 15 minutes break and then we'll continue.